Okay, so in this video, we are considering the second problem about related rates on the first problem sheet. We've already been through an example together, so we can go through this one a little quicker. Remember to visualize the problem, write down what you know and what you want, find a relation, differentiate, and then solve for the rates that you were trying to find. So we have a rocket rising vertically from a launching pad. So imagine that we're launching a rocket into space. So let's try and visualize this. Suppose this is the ground. The launching pad says here, and we're launching the rocket vertically. So the rocket will move up into space, and of course, a variable obviously is the height of the rocket as a function of time. As time goes on, the height is increasing, so we have here a variable. Suppose a rocket after some time is now here, so that's our rocket, and this is the height, which is a variable. Call this h. Good letter for height would be h. So this is our launching pad, this is our rocket. What else do we have? We have a computer-controlled camera on the ground 4 kilometers from the pad tracking the rocket. So it could be 4 kilometers to the left or to the right. It doesn't matter. Suppose the camera is 4 kilometers to the right of the launching pad, and the camera is on the ground. So suppose it is here. And we're told it is 4 kilometers from the pad. So this will be a constant. It will never change. The launching pad is fixed, the camera is fixed, and so this is 4 kilometers. And you see, in the previous problem, the units of distance were in meters. Now they will be in kilometers. What else do we have? What we know is that the camera is tracking the rocket. So imagine that as the rocket is moving up into space, the camera will always follow the rocket. So we're told here when the rocket reaches 3 kilometers, so when the height is 3 kilometers, the angle of the camera to the horizontal is increasing at a rate of 0.2 radians per second. And the fact that the angle is given in radians is really, really important. Remember that the derivatives that we have, the formulas we have for the derivative of trigonometric functions, are only valid for angles that are in radians. So every time you talk about angles, the odds are you'll be talking about trigonometric functions and their derivatives. So you always have to give the angles in radians. And we're talking about the angle of the camera to the horizontal. Well, again, the camera will always be shooting the rocket. Right? And of course, this segment, the angle and the length will change because the rocket is at first on the launching pad, the camera is shooting it, it's filming it, and then gradually the angle from the ground to the shooting ray will be changing. A good letter for an angle is theta. And now we have the situation. The rocket is being launched into space, the height is increasing, and so is the angle from the ground to the camera. The camera will always be following the rocket. Now we have captured all the variables of the problem. Let us write down what we know. So we're told that the angle of the camera, this is theta, to the horizontal, is increasing at a rate of 0.2 radians per second. Well, that is the rate of change of the angle in radians over time seconds. So that is exactly d theta over dt. The rate of change is the derivative. Rate of change of the angle, radians, over time, seconds. And the angle is increasing, and it's clear from the picture as time goes on, the rocket is higher and higher and higher, and so the angle keeps getting bigger and bigger and bigger. So positive rate of change, positive derivative, and that is 0.2 radians per second. And I'll just write RAD for radians per second. But we have to be careful here. This is not always the case. We're told that this is true when the rocket is 3 kilometers high. At this specific point in time, the angle is changing at this rate. So this is the rate of change of the angle as a function of time, specifically when the rocket is 3 kilometers high, therefore when h is equal to 3. And now that rate of change, specifically when h is 3, is 0.2 radians per second. At this moment, when the height is 3, we want the velocity of the rocket. Well, the velocity of the rocket will be the rate of change of h. So that's the derivative of h with respect to t. And again, at this moment, specifically when the rocket reaches a height of 3 kilometers. That's what we want to find. At this point, we forget the word problem because we have everything we need. We have the picture, we know what we know what we want, and now we're good to go. We need the relation now. We have to relate the angle with the height of the rocket. And the relation you will always find from the picture. Well, if you look here, because the rocket is being launched vertically, the angle to the ground is 90 degrees, pi over 2. So we have a right triangle. We have to connect the angle theta with the height h. So we have a right triangle, we have the angle, we have the opposite side is h, the adjacent is 4. Well, the trigonometric function connecting the angle of a right triangle with the height and the base is the tangent function. So SOHCAHTOA, tangent is opposite over adjacent. So tangent of theta is equal to h over 4, or if you prefer, 1/4 times h. Now we have a relation, and keep in mind that as time changes, h changes, so h is a function of t, and as time changes, the angle changes, so theta is also a function of t, where t again is in seconds. Well, both sides now, tan of theta is a function of t, 1/4 h is a function of t, so we can differentiate both sides with respect to t. Well, let's differentiate. This is tangent of theta. Well, the tangent is the outside function. The derivative of tangent is secant squared of what's inside theta, but be careful here. It's not just secant squared of theta because there is a theta left over, and we differentiate with respect to t. So by the chain rule, this is times d theta over dt. And now there's nothing left over, so we have the derivative of the left-hand side with respect to t equals, well, the right-hand side is 1/4 times h, but 1/4 is a constant multiple, so it just stays there, times the derivative of h with respect to t, that is dh over dt. And now we wanted dh over dt, so let's isolate dh over dt by multiplying across by 4. So the rate of change of the height of the rocket as a function of time will be 4 secant squared d theta over dt. And I'll write here secant squared as 1 over cosine squared. So this will be 4 times secant squared, but secant is 1 over cos. Secant squared is 1 over cos squared, so it's 4 over cos squared of theta times the rate of change of the angle, d theta over dt. So now we have the rate of change of the height for any given value of t. But if you remember, we don't just want dh over dt for any value of t. We want dh over dt specifically when the height of the rocket is 3 kilometers. So let's now look at the picture when the height is 3 kilometers. We'll have the same picture, but this will be 4, and now this will be 3. Let's see what we have from here. So when the height is equal to 3, the picture is the following. This is still 4 kilometers. This is now 3. And we have the angle. And since we want dh over dt when h is 3, we have to evaluate this expression when h is 3. That's what we wanted to find. So we wanted dh over dt specifically when the height equals 3. And that's equal to. Well, let's see. 4 is 4, so we'll have just 4 no matter what, times dh over dt, not dh but d theta over dt, when the height is 3. But this we know, right? When h equals 3, d theta over dt is 0.2. So times 0.2. And now all we're missing is the value of cosine of theta, then we'll square it, when h is 3. Because once again, we have to evaluate the expression when h equals 3. Well, think of it. If you knew the angle, you would then find cos of the angle, but we don't need the angle. We just have to find the cosine of the angle. Well, look at the picture. Once again, we have a right triangle. The height is 3, the base is 4. We can find the hypotenuse by Pythagoras' theorem. Right? The hypotenuse is the square root of the base squared, that's 16, plus the height squared, that's 9. But 16 plus 9 is 25. The root of 25 is just 5. And now we have a complete picture when the height is 3. The height of our triangle is 3, the base is 4, and the hypotenuse is 5. So we can easily now find cosine of theta. Cosine of theta, go back to your definition, and you see we don't really care what the angle is because we only need the cosine of the angle. SOHCAHTOA, cosine is the adjacent over the hypotenuse. So it's 4 over 5. Well, here we have 1 over cosine squared, so that's times 1 over the cosine squared. Well, if you square this, you'll get 4 squared, which is 16, over 5 squared, which is 25. And now we just have to simplify this expression. 4 times, if you want 0.2, that's 2 over 10, which is 1 over 5, so times 1 over 5. If you divide by a fraction, you multiply by the inverse, the reciprocal, so it'll be times 25 over 16, and we can simplify quite a bit here. Cancel the 4 with the 16, you're left with the 4 on the bottom. Cancel the 5 with the 25, you're left with the 5 on top. So all you're left with is 5 over 4. If you want, this is 1.25. And now we have our final answer. Let's give units. This was the rate of change of the height with respect to time. Well, if you recall, the units here of length were in kilometers, time was in seconds. So this is height, kilometers, over time over seconds. And you see, once again, we have a positive rate of change, which makes sense, right? Because that's the rate of change of the height of the rocket. And as time goes on, the height is increasing. And when you have a variable that's increasing, it must have a positive rate of change. And so our conclusion is, when the rocket reaches a height of 3 kilometers, its rate of change, its velocity is 1.25 kilometers per second. So there you have it.